So first of all, to who is in presence, I checked for the list of names last time, and despite I asked you to register your presence, I found that there were 18 persons in presence, and only 11 marked their presence in the Prodigy system. Next time, I have no time today, but probably at the end of class, I will check your names and see if you have correctly registered or not your presence. It's important, of course, for the well-known reasons. So we are talking about multi-stage vehicle in general, and this will apply especially to launchers. So we are trying to understand how to divide in stages possibly a vehicle, and we have seen that we can divide our vehicle in sub-rockets made of different stages. We have defined the parts that are called stages and the corresponding sub-rockets. And we have seen that we have two important, two general relations for this multi-stage vehicle that allow us to evaluate the overall payload ratio, lambda, which is mu over m0, and then, of course, the delta V. And this will be the product of the different lambda I, which are the payload ratio of each sub-rocket. Then we have the overall delta V, which is our target, that is expressed as the sum of the change of velocity provided by each of the sub-rockets. And these are the expressions that we have found last time. Now, what we can do is to find, as I mentioned yesterday, the optimal partitioning in stages exploiting the Lagrangian multiplier. And what we said is that in general, we should aim to get a given delta V, and would like to consider a multi-stage option to improve our lambda, to get the maximum lambda as large as possible. So we consider that we can find a constrained optimum, considering, for instance, our function of lambda, of the different lambda I, which could be, for instance, our lambda, which is a function in terms of lambda I, is this relation, plus a term which is our side condition that tell us that our delta V should be given by this expression. So delta V, this is a number, it's a constant, let's say minus delta V. This is a constant, and this is the expression of delta V as a function of the different lambda I. And so we can make this derivative, the f over the lambda I, equal to 0 to find our optimum. We can proceed equivalently in a different way, saying that our g of lambda I would be This expression here is a similar one. In this first case, we are imagining that we are optimizing our lambda with the side condition on delta V. So we are finding the maximum lambda. In this other expression with this function g, we are looking to the maximum delta V for a given lambda, which is in the side condition between brackets. Yes, if we make the derivative, you see immediately that is the same. Okay. We can better write these equations exploiting as we have a product here, everything becomes simpler if we consider the logarithm of lambda. So that we transform the product in a sum. And so we can look for the maximum of this logarithm. And also to change here, instead of considering the function lambda, considering the logarithmic function. And if we do this, let me just add here, change here these expressions, and see another pair of functions we can write here. That's logarithm of lambda here, and and here I have to rewrite it. So g lambda I would be delta V plus beta sum of the logarithms of lambda minus lambda. So we have these two. And now if you make derivatives, you will have here one derivative with respect to lambda I. Here we have 1 over lambda I. And here we have the derivative dv, the lambda I. So again here we have 1 over lambda I, and here the derivative of delta V over lambda I. So at the end, what we have is that alpha and beta are just one the inverse of the other. So it's a number that, depending on what you choose, is just a number that will be determined later, but you see evidently that actually it's the same procedure. So say this, we will follow now, even if we are looking to the best lambda, but we write, for the sake of convenience, this expression here, this g. So we consider the g lambda in d lambda equal to 0 for all values of I, and we can take the expression I just wrote here. We make derivatives with respect to lambda I here, so this will be minus specific impulse of the subrocket, and then the inverse of the argument of the logarithm multiplied by 1 minus epsilon I. So we have that our dg d lambda we say that is 1 minus epsilon and 1 minus epsilon plus 1 minus epsilon lambda. And then we have the Lagrangian multiplier alpha. And you see here, sorry, beta, or call it alpha, that's the same. Be easier for me to avoid confusion. This multiplies by the Lagrangian multiplier by these terms between brackets that this is a constant, so the derivative is 0. Here we have the logarithm, the derivative is just 1 over lambda. Okay. And this is, of course, is a set of equations, n equation, one for each subbracket. So at this point we can solve for, we are looking for the values. So what we assume that each subbracket is characterized by a given specific impulse, u equivalent 1, u equivalent I, and by the other aspect of proportion that we know is our inert mass fraction epsilon I. So we have this information, and from this we are looking for the n values of lambda that give us, for a given delta V, the maximum payload ratio. So we try to solve for lambda, and we have that lambda that multiplies here u and 1 minus epsilon is equal to alpha epsilon plus alpha 1 minus epsilon lambda. And so from here we obtain that lambda is equal to alpha epsilon, and our denominator we have 1 minus epsilon I that multiplies. So I'm bringing everything on the left, so it will be UEQ I minus alpha. Okay. So we have found our expression for the different payload ratio, which will depend on the Lagrangian parameter alpha. And so we still have to know what is alpha. And we can obtain this value of alpha by the side condition. So the side condition is our constraint, the relation between the fact that the product of the different lambda will have is the one in parentheses, this one. So this is our side condition, and we can enforce this to find our value of alpha. So we just replace here this expression, just written for lambda I substitute in this one, and I can write this in this way: sum I from 1 to n, and we have the different terms is a product, so that we can express in a sum of different logarithmic terms. and this is the denominator will be this one. So in general, we found a nice expression, but we still don't have the value of alpha. The value of alpha here, actually you have that these are logarithms, so there will be if you want to come back to algebraic equation, you will have a product of different terms with alpha, and so you have an equation of high degree in alpha, and in particular should be an equation of order n in alpha, so you have n solutions in general, and one could be better than the other. And this can be, of course, found with suitable numerical approaches. But if we are aiming to understand what it will be the partitioning among different rockets, let's consider some special case where the solution can be found analytically. So a first interesting case is the one that considers the same specific impulse for all the subrocket, all the stages. So in this case, we have that we can bring outside the summation here, this term and this term, because it will be u eq I is equal to the single value u eq. So in this case, we'll have that logarithm of lambda is equal to, we see here we have alpha over ueq minus alpha, and is the same terms summed n times. And then we have the term related to the different inert fraction of the different stages. And here. So from this equation, we can go back to alpha and then to lambda I for each stage. So we can obtain this term here that is the same that appears in this expression. We have alpha over ueq minus alpha. So what we can do is to obtain this expression. Let's consider this logarithm n times, or this to the n power is the same, will be logarithm lambda over this sum. No, sorry, I'm doing something wrong. One step at a time. Logarithm lambda minus sum So this is what I wanted to write. And then I pass to the expression without logarithm, and this is lambda that divides this term, or that multiplies the inverse. And at the end, we obtain this is 1 over n. Okay, we can at this point go back to the expression of lambda I, where we have exactly this term multiplied by epsilon over 1 minus epsilon. And we write that lambda as this expression. So that we have found our solution. Found our solution where, however, we see here the term lambda. It was actually our goal. So in this case, if we take this expression, we put them in the value of in the expression of delta V, we have the maximum delta V for a given lambda. But we can invert this relation and express the value of lambda as a function of the delta V and of the number of stages, provided that we have the same specific impulse for all the stages and given the values of the inert mass function of the stages. So when I make the substitution in this expression of delta V, I have to put here the value of lambda I. So I have the sum, the logarithm here, and then epsilon I plus 1 minus epsilon that multiplies this term. So actually, I can also avoid to write here 1 minus epsilon because it cancels with this one here, and it remains just epsilon before this parenthesis. Now let me also adjust this. That will be our lambda and then pi j equal 1 to n, 1 minus epsilon j over epsilon j, 1 over n, close parenthesis. So as usual, I can split product in express them in sum using the logarithm, and here it becomes minus uq, and then I have sum because here I can extract here the epsilon, which is common to terms, and so this becomes epsilon I multiplying something else, and so the epsilon I is brought outside, And then I have again the sum I equal 1 to n of 1 plus lambda and this no longer parentheses. This is 1 over n. Okay, the term in parentheses is this one. Yes, what we see here now is that this term in square bracket, bigger square bracket here, is the sum of terms which are all independent of I. So this is n times the term between square brackets. And so this is the sum of, this was a logarithm, is the sum of n times the logarithm, means the quantity, the argument of the logarithm to the power n. So it becomes again minus ueq sum logarithm of epsilon I plus, now it's logarithm of 1 plus lambda this is 1 minus epsilon over epsilon. All these terms are to 1 over n, and close square parenthesis is at the power n at this point. This allows us to get lambda. That will be, now I can divide here delta v over u. There will be minus this sum. And then I have this logarithm, so I can make the power of this other quantity, and I can get the inverse of the logarithm, and so the solution for lambda. Actually, I have here we can write that delta v over eq minus is equal to the logarithm of the product I equal to 1 n of epsilon, and then the term in square brackets to the power n. This is what, of course, this term in square brackets is the one that was before under the sign of logarithm. So from here, we had here 1 plus lambda product, blah, blah. So we can obtain our lambda, making that e to the power delta v over ueq is this product that multiplies 1 plus lambda product j equal 1 to n, and it was 1 minus epsilon over epsilon. Everything here 1 over n, and here to the power n. So now we can separate things, and here in particular this will be divided and brought to the power 1 over n, epsilon I, so which is okay, 1 over n, and this is equal to 1 plus lambda 1 over n, and the product, let's put now as I, also to the power 1 over n. And so from this we can get the final result, which is the following. So consider that from here we have this one, so we have to be careful, but we bring this one here and we have this parenthesis minus 1 on this side, and then I can make the n power of everything to get lambda. So so this will be, we have considered that there was a denominator, so where it was 1, now there is pi equals 1 to n epsilon I, and all this is to the power n, and a denominator I have this. So what you have done, let's try to, here I have that this one goes to the left-hand side in this way, then I divide one over n for both, then we do this to the power n, everything to the power n, and finally I make the common denominator here, and I have the difference of these two quantities to this power, and then here 1 over n, and then simplifies, and this product can be simplified with this one. So we found a solution that can be used, provided we have the same specific impulse and different. And it can be considered for a given delta V. We found the final value of lambda. You can check with different cases. You can make an example, for instance, for 2 stages and check if we improve or not our payload ratio, considering perhaps the same or different values of epsilon. It's particularly straightforward, the solution, if you consider also that we have a single value of epsilon. Let's call this as the epsilon of the stage. And in this case, our lambda I, it was epsilon 1 minus epsilon lambda and product of 1 minus epsilon over epsilon, this to the 1 over n. If we consider the same value of epsilon for each stage, this lambda I will be epsilon over 1 minus epsilon that multiplies lambda 1 over n, and then we have to multiply n times 1 minus epsilon over epsilon. That will be 1 minus epsilon over epsilon to the power n, and this must be then to the power 1 over n. So we can see that is exactly 1 minus epsilon over epsilon. It simplifies, and we have this special solution that tells us that for this special case, lambda I is equal to lambda to the power 1 over n. And for each value of I, so all the stages have the same payload ratio. In this case, we have, in practice, we call these stages as similar because they have the same inner mass fraction, the same payload ratio, and they will provide, of course, with the same epsilon, with the same lambda, and the same specific impulse, will provide also the same delta V. So we have that each stage provides the same delta V, and the final delta V will be delta V equal to n times delta V stage. From this, we can also write now this expression for this special case, and we have just to substitute the case of n times the value of the stage here and here. So here what we see is that there will be epsilon to power n and 1 over n, so we remain just epsilon. And at the denominator we have 1 minus epsilon n times, so it will be to the power n. So for the special case of similar stages, we have that lambda will be equal to E minus delta V over n UQ minus epsilon stage over 1 minus epsilon stage to the power n. So we can analyze this function. So we have a general solution, a second level solution where we have the same specific impulse, and final third solution with similar stages. We go with different steps of simplicity, and we try to understand how this lambda behaves in the simplest case by changing the value of n, so by increasing the number of stages. And what we see that if we plot, we cannot do this because, of course, n is not a continuous variable, it's a discrete one, but we can, in principle, see how this function behaves, and we can easily see that we have a behavior of this kind. We have that our goal is in fact reached by increasing the number of stages, because as we jettison our useless masses once the propellant that they had to contain has been used, we no longer have to accelerate these discarded masses, so we can improve. We can provide the same acceleration with a lower propellant mass for the actual payload. And so we see that these curves increase, but by this drawing, and you can see it better if you put numbers in, we see that actually the change occurs, especially at the beginning. If we pass from 1 to 2, for let's say, for the first cases, 1, 2, 3, 4 stages, then we go asymptotically towards a value. So we are increasing complexity of the launcher without having a special convenience in terms of final payload ratio. We also see here that we can also, considering this as a continuous function, we can find the limiting value, the asymptotic value that we found for n infinity, and yes, this can be, what we see here is that for n goes to infinity, this term goes to 1, so this will be 1 minus epsilon over 1 minus epsilon, means 1 to the power n that is going to infinity. This is a form that cannot be evaluated, so we can pass to the, we have una forma indeterminata, I don't have the word, so it cannot be solved, and at this point, but we have a finite limit here. So what we can do is to apply to the theorem of de L'Hopital and obtain the solution. The solution is, so I can pass to the logarithm, and this will be n logarithm of this term in parentheses, and to eliminate the indetermination, I have to consider this logarithm of over 1 over n. So in this case, we have 0 over 0, which is an undeterminate form, and so we can make derivatives of numerator and denominator and get the final solution, and this would be minus 1 over n squared, and here I have that it will be 1 minus epsilon, and then here I have delta V u e q, and it will be 1 over n squared, and of course by the same E minus dV and u e q. So this can be now cancelled, and goes to infinity. This is 1. And so we find that our logarithm of lambda for n that goes to infinity is 1 minus there is a minus in front, is this one. And so we have found the limiting condition, which is the following. Is just an exercise, because of course m doesn't go to infinity, but we will make also some further consideration on this, because there can be something interesting. What, however, we are seeing now is that this kind of staging seems to be always better and better to go towards a high number of stages. Also, we see here that lambda as a function of delta V over U and Q (0 and 1), delta V equal to 0, of course, lambda is equal to 1. But as we move towards increasing delta V, we see that we have increase of lambda. And you see from this plot that what you cannot do given delta V, that cannot be done with a given value of n, can be done with another value. So you see, for instance, that this delta V here is not achievable if this is 1, this is 2, this is infinity. It's not achievable with 1. It will be achievable with 2, and of course even better if we move towards infinity. And this same plot is also sometimes given in a log form. With, of course, the limiting value, which is this 0 here for lambda. Where we actually see that we have, given the fact that we have an epsilon, we have that we cannot realize any mission, so delta V. In terms of epsilon, we see that, of course, as we increase epsilon, we are decreasing our payload mass function, but this is rather straightforward. So I can stop 10 minutes, and then we will resume. Certamente. Prego. Vediamo un attimo. L'algoritmo in base 10 di lambda. Se facciamo ln lambda è uguale a meno su 1 meno epsilon, e quindi in realtà non sono delle rette, sono ce l'ho disegnato così, ma direi che sono... Ah no, sono delle rette, scusi, perché in funzione sono delle rette a pendenza negativa, perché sono logaritmo di lambda in funzione di delta V, e quindi però il coefficiente angolare cambia con epsilon. Sì, sì, soltanto che prima abbiamo visto dei grafici con di lambda in funzione di delta V per un certo valore di epsilon con n a parametro. Questo è invece il valore per un certo valore di n, o meglio, avete fatto bene a farmi questa domanda, questo è infinito, ecco. Infatti io stavo guardando l'equazione, questa qui, è quella che sto graficando, quindi quello è il massimo valore di lambda che può essere ottenuto, quindi per n che tende a infinito, al variare di epsilon questo massimo cambia. Grazie della domanda. Si vede che la presenza aiuta le domande. So we can start. Just give a minute for everybody to be ready. Just a couple of consequences of these results in terms of other parameters. We can see that the propellant mass fraction, the overall propellant mass fraction would be mp over m0, and this can be expressed by splitting the different terms in the different subrockets so that we make appear the propellant mass fraction of each subrocket. So we can, this will be the mp1 over m0 plus mp2 m01 plus blah blah. This is the one for sure, the first step. And then we have other terms which are of the kind mp2 over m0 1, that should be written as mp2 over m02, m02 over m01, and this is the lambda 1, and this is zeta 2. And so what we see here is that if you go ahead mp3, there will be lambda 1 and lambda 2, and so on. So that we can write sum I equal 2 up to n zi pi j equal 1 to I minus 1 lambda j. This is the general expression. And in the special case with similar stages, we see that we have similar stages, so the same value of the propellant mass fraction for each stage. And then we have to consider here 1, and then second term will be lambda 1. The third term will be lambda 1, lambda 2. Fourth term lambda 1, lambda 2, lambda 3. And so on, up to lambda n minus 1. This comes from the fact that all stages are similar, so they have each stage has the same ratio of different masses. So this sum can be expressed as known as follows. And you know that this lambda s to n is exactly the overall lambda. So this becomes zeta 1 minus lambda over 1 minus lambda s. We also recall that for, by definition of the different ratios, we have that zeta is 1 minus epsilon 1 minus lambda. And so we can obtain, by placing here 1 minus lambda cancel with this one, we leave 1 minus epsilon and 1 minus lambda. So we have that also here for the overall z is exactly the same expression. but with a larger lambda, which is the overall lambda. And so we see that in this case, this ratio does not depend on n, provided that the stages are similar. And we can also see that, I'll not show it here now because of time, but the epsilon will be, the overall epsilon will be equal to the stage epsilon. You can show it, of course, defining this as the ratio between the mass of the inert mass over the inert plus propellant masses. Let's make some general consideration now on what we have found. I go back to these expressions. This means n stages will be, we are considering similar stages. Okay, I have these three expressions. We have seen now that for a launcher, we have to get a delta V. To reach the orbit, we need the delta V order of magnitude 9 kilometers per second. On the other hand, at the best, very best, so idealized for the moment performance of a chemical rocket, we have more or less 4.5 seconds, kilometers per second as the specific impulse. So let's consider this optimistic case. So we see that this ratio is 2, more or less. 2.0. So now let's use this value inside these expressions, and let's see the limiting case. First of all, this is of course also the mass ratio. We have delta V equal minus UEQ logarithm of mr, so mr is equal to E minus delta V over EQ. This is now equal to 2, and in this case, mr is about 13%. So with this data, we have that the final mass would be slightly more than 10% of the initial one. And this means that the remaining 6.5%, this is for a single stage, is propellant. And actually, to get this specific impulse, we need also huge tanks, so also the cryogenic propellant. So the fact of having this final mass ratio, the final mass so let's say small with respect to the overall one, means that more or less it will be all structures, no payload. We can see, in fact, that if we assume the limiting condition of a single stage with lambda equal to 0, of course, this means that should be epsilon equal to 13.5%. That is actually, it's not so easy. It's at the limit of today's technical capabilities with zero payload. If we now consider, let's consider now two similar stages with the same technological capability. That means, let's say, with the same epsilon. And let's see what are the figures. In this case, we have that delta V for each stage will be half. So it will be delta V1, delta V2 will be equal to 4.5 kilometers per second. And from here, and this expression, I can obtain the corresponding Z1, Z2, that will be equal to 63.2%. So if you see this and put things together, you see that the overall propellant mass is now only, let's say only, 80%. That means that we have now 12.6% for the inert mass and 7.2% for the payload. So what changes here is that we move, the overall Z will be 80.2%. We have all the needed formulas available. And now lambda is 7.2%. So we pass from 0 to 7.2%. Now, with the same, let's say, technological capability. And of course, we can even improve if we go towards the infinite number of stages. Before going ahead, I would like to make a further comment on this. Because actually, when we consider an infinite number of stages, we are dropping our tanks together with the propellant. So what we can do to get this expression is also to consider that the mass of the rocket is changing not only because we are delivering propellant, but also because we are delivering tanks or masses. So we can say that this expression is equivalent to say that our mass variation in time will be given by the propellant mass flow rate through the rocket, but we have also to consider that we are changing the inert mass, and these all quantities are less than 0. dms dt. Or we can write this also as d dt mp plus ms, and these is also a term less than 0, so that we know that dot mp is minus dmp dt, and this in turn can be expressed through the epsilon as minus dot mp over 1 minus epsilon. So if we use this in the rocket equation, where we have mdv dt, the mass by acceleration of the vehicle is equal to the applied force, which is dot mp ue, we can substitute this expression of dot mp now, and will be 1 minus epsilon. And here I have UE, and then dm dt. So if you integrate by parts now, you see that we have dm over m that is no longer just ueq, but also 1 minus e st. So we obtain from here our mass ratio, that in this case will be equal to, I put here already here inside the structural mass, so this mass ratio here is all the period mass fraction, and will be now E to minus delta V over ueq minus E epsilon st. So just if you compare the equation, just the difference is this term. So you see that is equivalent. Just this was a note that I would like to give you. And going back, we can also consider different kind of rockets. If you consider solid rockets, we would have lower values of specific impulse. It could be 3 kilometers per second. It means that with a single stage launcher, we would have a 95% of launcher made by propellant. And this is impractical, of course. What is the fact that we have not considered so far, where strong hypotheses have been done in this analysis? There is one which is important, is that especially when we are considering the variation with a number of stages, considering a given value of performance in terms of specific impulse and inert mass fraction, we are making a strong assumption. Because when we talk about inert mass fraction, we are talking of something that, say, we are assuming that the inert mass changes according to the propellant mass we have seen last times. This is not always the case, because we should consider that this is true if most of the rocket is made of propellant. So in these cases, it's reasonable to think that most of the rocket is made of propellant, the structures, and so the inert mass available would be proportional to the propellant mass fraction. What happens is that if we move towards more and more stages, if we increase n, the amount of propellant of each stage decreases. But each stage has, for instance, its control, its separation devices, its engine. And so we should consider that the relative amount of mass that would be proportional to the propellant for each stage will decrease as we move towards a higher number of stages. This makes that the considerations we have seen before about the fact that as we increase n, we have always an increase of overall payload ratio is no longer valid and actually is not true. We should consider, in fact, that our inert mass should be made of different terms. I just would like to underline different contribution now. We can identify three contributions at this moment. One is the contribution we have seen so far. It's a contribution of inert mass which is proportional to the propellant mass. Another part, which is a mass which is proportional to, it's not proportional, is the mass of the engine, and other masses which are, for instance, controls and other devices. So what we see here is that we know how to express this dependence. Proportional to MP. We can make also a reasoning about this second term, which is the mass of the engine. Probably this will scale with the thrust level. The larger the thrust, the larger will be the size of the engine for a given kind of engine. So with given also specific parts, if we are making the comparison at the same performance level. And so the thrust will scale with the size, and also with the mass of the engine will scale accordingly. So we have two different scaling factors here, thrust and propellant mass, and then we have some other things that we will neglect now, that are masses which are not dependent neither on thrust, neither on the propellant mass. So, and we can also try to make a further step and say what will be the thrust level that we have to consider for each stage. If we make consideration about the accelerations, we can reasonably consider that thrust will be roughly proportional to the stage mass, or better, to the subrocket mass. So we can take as the reference the mass of the subrocket at the beginning of operation. With this assumption, we should therefore consider that for the generic subrocket we have MSI. We have a contribution proportional to the propellant mass, and another contribution, let's say through a K E, meaning for the engine, that multiplies the initial mass of that subrocket. So with this we can, now I will not make all the steps, but we can make some of the steps needed for the definition of the contribution of different stages, and by just changing something, because if I define now our mass ratio, which is always 1 minus the propellant mass fraction, so this is also the final mass over the initial mass of the subrocket. This final mass will be payload plus inert one. So this will be, of course, our lambda, mu over m0. And then we have this ms that will be now expressed. The first one in terms of propellant. So through the propellant mass fraction, and the other term is just proportional to m0I, so it's simplifying, it will leave only k EI. So what happens here is that we can try to express now the mass ratio as a function of epsilon, lambda, and k. From the above expression, I can just multiply left and right by 1 minus epsilon and obtain this lambda I plus k ei 1 minus epsilon. And so we have 1 minus z, which is mr. So mri is epsilon plus 1 minus epsilon lambda plus kei. So you see that what has changed in this expression with respect to what you have seen before is the presence of this additional term to lambda. Where there was lambda, there is now lambda plus k. And so we can make the optimal partitioning again. This time we have to consider these two expressions. With the, well, this is the side condition, and this is the equation for the different lambda. So let's consider directly the case with similar stages. So it means same specific importance, same factors, same k, same epsilon. So in this case, the equation for delta V will simplify. Sum I equal 1 to n. Now we have here epsilon plus 1 minus epsilon, our unknown, which is lambda I, plus ke, which is also the same for all stages. We can pass again through the Lagrangian multiplier, and you see that we have just, for derivative, we have just to consider this k aside of our lambda. So you have minus ueq 1 minus epsilon over epsilon plus 1 minus epsilon lambda plus k. So consider that we are going straightforward to the case with similar stages. So we have the expression ready for that. And we don't want to spend too much here because we see that, of course, this expression tells us that our lambda I is the same for all stages. It comes obvious because all other terms are not depending on I. So this means that lambda I is equal to lambda 1 over n. And so we can go back here and say that this is lambda to power 1 over n, and then I can extract this value from this expression, and in particular I write e to minus delta v over n times uaq. Of course, all term under summation is the same, so you sum same terms n times, and this n goes here. And this is what is obtained just considering that expression of delta v. I obtain from here the value of lambda, is e alla minus delta v over n uq minus epsilon over 1 minus epsilon minus ke st. To the power n. You see, it's similar, but it's different because we have this k now. And in fact, you can go back to the former expression if you consider k is equal to 0. You have e minus epsilon, 1 minus epsilon. And in fact, in that case, you recall that for n that goes to infinity, you have 1 minus epsilon over 1 minus epsilon, which is 1 to the power n, give you an undeterminate form. On the contrary, let's consider the opposite case, the other extreme. The case where qualcuno ha aperto il microfono? Let's consider the other extreme, which is the case where we have epsilon equal to 0, k different from 0. So the inert mass is only depending on the thrust level. If this is the case, you would have this expression. E minus delta V n uq minus k. This is with epsilon equal to 0 and k not 0. So what happens here is that if you consider n that goes to infinity, this is 1 again, but we have 1 minus a number. So it's a number to the power infinity, or better, yes, it's a number less than 1 to the power infinity, and so it's 1 over infinity. That means that for this term, lambda now infinity goes to 0. So you see that something changes, because at the end, we are increasing more and more the mass of overall the number of engines that we have on board. And so it means that we are wasting mass. We are no longer saving masses, but we are adding further and further masses, reducing the room available for the payload. So, of course, we can consider also the real case will be something that includes both contributions of the masses proportional to the thrust level and the masses proportional to the propellant mass. So at the end, what we see is that we have lambda as a function of n. It was something like this for the k equal to 0, ke. We have something like this in this case. So when epsilon and we have something in between in the more general case, where we see that we have this time some conditions. Let's say that we have an optimal number of stages. Let me try to show you this. So if you see this drawing, this plot is just you have different number of stages, 1, 2, 3, 4, 5, 6, 7, 8 for a multi-stage rocket payload mass fraction, and we have I've considered just a representative value of something. I put a value of E minus delta V of over EQ, and then I consider 0.05 and 0.05 in the intermediate case for epsilon s and ke, or 0.1 if everything is proportional to the propellant mass or to the engine. So what you see here, I would like that I would like to bring your attention to the difference between 1 and 2 and the differences between 2 and the others. So you see that, of course, this will depend also on the delta V you are analyzing and on the specific impulse and all the mass ratios. But for the case that I selected, you see that there can be a huge difference between the first two cases, and then you have this flat behavior in case you have no dependence on the thrust level. The orange corresponds to the case where we have just dependence on the thrust level, and the gray one is something intermediate. So you see that in these cases, for the blue bars, you have that the higher the number of stages, the better. For the orange lines, it should be probably 2, and for the gray line, gray bars, the best is corresponding to 3 stages. No? So I have to conclude now, but we will see a further example, and I will we'll see. We still have a couple of things to do about staging. The first thing that we have to consider is the case where we have a different specific impulse. We have not considered this so far, but we can consider for 2 stages. And in case we have the same epsilon, we can try to make a comparison. Probably you can do it also by yourself as an exercise. And we can consider, for instance, something like resembling the Falcon 9, where we have consider ISP 300 seconds, 1 and 2 for the first stage, and 350 seconds for the second stage, and we assume that we have the same epsilon, 0.1, 10%. We have to realize delta V 9 km per second. And we can try to see what happens, how partitioning. So we assume that delta V1 will be a fraction of the order of delta V, and delta V2 a fraction, the remaining fraction. So in this case, what we have, of course, lambda will be lambda 1 by lambda 2, and lambda 1 is E minus delta V1 over U Q1 minus epsilon S over 1 minus epsilon S, and similarly so you have everything, and you can see, for instance, the value of lambda as a function of x. And try, and if I go here again, should be this. So these are different plots obtained with different assumptions, really. The case where we have, these are the 2 stages. On the abscissa there is the x, and on the ordinate we have the lambda. And here you see this first curve is obtained considering the same specific impulse. We have already the same epsilon. If you consider also the same specific impulse, 300 seconds, we optimize here, which is at 50%, of course, similar stages. And this is also true if we consider the higher value of specific impulse, which is this one. If we have different values of specific impulse, we have an intermediate curve, and you see that the optimum will be here, that is at position that corresponds to having less contribution for the first stage, which has less specific impulse, whereas the contribution of the second stage will be greater because of the higher specific impulse. And so we have more or less 42% for the first stage, and the remaining 58% for the second stage, for this difference 300 to 350. So I conclude today's class here.